Hello and welcome back to the fourth chapter in our course on cryptography. Today we will talk about the basics of private key encryption. As a complementary read for this segment, I recommend chapter 3.1 and 3.2 of the book of Katz and Lindell. In the last lecture, we've seen that perfectly secret encryption necessarily will have long keys. That was the statement of the theorem of Shannon. In a perfectly secure encryption scheme, the key must be as long as the message, and it cannot be reused. However, if we think a bit about it, perfect secrecy is an overkill. We don't need security against unlimited and unbounded adversaries. Security against adversaries who are reasonable or realistic in a certain sense would be sufficient. Also, is secrecy alone sufficient? What about other types of attacks? This is not captured at all by the notion of perfect secrecy. Let's look at an attack which doesn't even break secrecy. Say two armies, one on the right here and one on the left here, want to attack a castle. And in order to defeat the defenders, they both need to attack at the same time. Both armies share a secret key K, which they are going to use to encrypt a message under the one-time pad. Now, let's say the commander of the first army on the right made up his decision and encrypts his decision to the general of the other army. Let's say MB is the message he wants to send. Then he gets a ciphertext C. Now he wants to send this ciphertext over to the other general. Whoa, but wait a second. The messenger is intercepted by a spy of the defenders. Let's say the defenders know that this ciphertext C encrypts either a message attack or a message wait. So what this spy of the defenders does is it takes this ciphertext C and XORs both M0 and M1 onto the ciphertext, getting a ciphertext C prime, and forwards the ciphertext C prime to the second general. So what happened now? Let's say the ciphertext C encrypted the first message. So C is K XOR M0. Then C prime is K XOR M0. That's just C XOR M0 XOR M1. But M0 XOR M0, that's just the all zero string. So this is K XOR M1. So that means the second general got a correct encryption of the message M1, which says wait. That means the first general is going to attack, the second general is going to wait, and the defenders are going to win. All right, so back to our problem of constructing secret key encryption with messages that are shorter than the key. The main idea here is to limit the runtime of the adversaries. Recall that the notion of perfect secrecy held against any adversary that had any unbounded amount of runtime. This is clearly not a realistic limitation of an adversary, so let's try to limit adversaries in terms of their runtime. That is, we will define a notion similar to perfect secrecy, but only consider computationally bounded adversaries. Henceforth, we'll assume that the adversary is upper bounded by a realistic upper bound on its runtime or on its operations. Say the number of operations T is upper bounded by something like 2 to the 80, which is a figure that you'll often see in cryptanalytic discussions. So now we'll modify the definition of perfect secrecy to only account for adversaries whose runtime is bounded by T. Let's take again our int experiment that we saw in the last lecture. Recall that in this experiment, First, the adversary announces two messages, M0, M1, to a challenger. The challenger generates a secret key, chooses a random bit B, and encrypts the message MB, getting a ciphertext C star. The ciphertext C star is sent back to the adversary. The adversary is allowed to do any computations. Now the adversary will only be allowed to do computations that are T-bounded or to have runtime T. And at the end of this, the adversary outputs a guess B prime. If B prime equals B, the adversary will, the challenger will output 1, otherwise 0. And we call the variable denoting this output just int A. So now we say that an encryption scheme, keygen enc_dec, is T insecure if it holds for every T-bounded adversary. So not for every adversary, but only for every T-bounded adversary, that the probability that this experiment outputs 1 for such an adversary is exactly 1/2. So let's ask ourselves, is this a good definition? To see that this is not a good definition, we don't have to go further than last lecture. Recall the second step from the proof of Shannon theorem, where we showed that definition 3 implies definition 2. If a encryption scheme is not perfectly secret, meaning if definition 2 does not hold, then there exist messages M0, M1, and a ciphertext C, such that the probability of obtaining C when we encrypt M0 is larger than the probability of obtaining C when we encrypt M1. What have we done with this? Well, we've constructed an adversary A against the int experiment. This adversary did something very simple. It just checks if the challenge ciphertext is equal to C. If so, it will guess B prime equals 0. Otherwise, it just sends a random bit. And we've showed that this adversary has a success probability of greater than 1/2. But now look at this. This adversary here doesn't do anything complicated. It's just an if-then-else clause. So this adversary here has constant complexity, meaning that we cannot defeat this adversary here by bounding his runtime to something like 2 to the 80. So something is missing in our security definition. A good security definition should account for the fact that such a computationally bounded adversary A could be able to win this int experiment with probability greater than 1/2, but not by a lot more than 1/2. So we introduce a new parameter epsilon, which we call the advantage. The experiment is still the same as before, but now the definition says the following. An encryption scheme keygen enc_dec is T epsilon insecure if it holds for every T-bounded adversary that the probability that this adversary wins this experiment, this int experiment, is at most 1/2 plus epsilon. And we call this security the security definition T epsilon insecurity. All right, so now we have a notion of concrete security, but how do we actually determine if a scheme is T epsilon secure? In practice, we do this via cryptanalysis. We choose the parameters of the scheme in such a way that the best known attack will have time complexity T and an advantage less than epsilon. Parameters we target in practice are often T equals 2 to the 80 and epsilon equals 2 to the minus 60. What's actually the unit of T? Is it like milliseconds or elementary CPU operations or maybe CPU cycles? And what type of CPU is this? Is it like an Intel or an AMD CPU? So you see there's much of headroom here of how the unit of this t could actually be defined. What about other models of computations? You don't have to go to exotic models of computation like quantum computing. You can go to other analog computational models like optical computers. How do you measure complexity there? Well, it turns out concrete security is really inherently technology dependent. So the question is, how can we reason about security in a way that we make a statement in any reasonable computational model? So we don't want to tie our security notion to a fixed computational model, but want to be able to make statements about all reasonable computational models at the same time. We will do this via asymptotic complexity or computational complexity theory. Recall, in complexity theory, problems consist of an infinite number of instances. And we measure the complexity of an algorithm solving some problem as a function of the size of the instances being given, or more generally, some kind of size parameters. For instance, take sorting as an example. Merge sort has a complexity or a runtime complexity of n log n to sort a list of n elements. Here n is the size parameter. And recall that we generally say that an algorithm is efficient if it runs in time poly n. This leads us to the concept of asymptotic security. The idea is to introduce some parameter lambda, which we call the security parameter, which characterizes the hardness of breaking a scheme. And just as complexity theory only cares about what happens when the size of instances grows towards infinity, we will only care about what happens when this security parameter grows towards infinity. We will now modify the keygen algorithm to take this security parameter lambda as an explicit input. We typically write this in unary as 1 to the lambda. Moreover, we will now identify efficient computation with probabilistic polynomial time algorithms. That is, algorithms which run in time poly lambda. So efficient adversaries will be PPT machines. But what about the advantage epsilon? Should it be exponentially small? That might be an overkill. But it should definitely be smaller than 1 divided by poly. But which polynomial? Well, as we'll see, for every polynomial and every sufficiently large security parameter. This motivates the notion of negligible functions. Function f mapping from the integers to the non-negative reals is called negligible if for every polynomial p there exists an integer capital N such that for all integers small n greater capital N, it holds that f of n is smaller than 1 over p of n. How can you think of this? Well, take a negligible function f, has some behavior for small values of n, but then as n grows, it goes quickly towards 0. So if you take any inverse polynomial, at some point, here would be our n, our capital N, this polynomial or this inverse polynomial 1 over p of n is always greater than f of n. Two quick remarks. So when we want to check if a function is negligible, it suffices to look at polynomials of the form n to the c for a constant c. Such polynomials are called monomials. And generally, we will write a negel of n for an unspecified negligible function. Let's look at a few examples. First one is 2 to the minus n. Is this a negligible function? Yes. We know that exponential functions decay faster than any inverse polynomial. Maybe to see this in more detail, let's say 2 to the minus n smaller than n to the c, n to the minus c. If we take the logarithm on both sides, we get, this is equivalent to minus n smaller than minus c times log n, which is of course equivalent to n greater than c times log n. But as we know from our math classes, the linear function n asymptotically grows faster than the logarithm. Even if we scale the logarithm function up with a constant c, n still grows faster. If you want to prove this in all details, this can be proved via the rule of de l'Hopital. Second function, f2 of n is n to the minus 100. Is that negligible? No. This is an inverse polynomial. It's of the form n to the minus c, or 1 over n to the c, where c is 100. So this is an inverse polynomial. This is not negligible. Next one, 2 to the minus log n. Is that negligible? Well, the answer is still no. 2 to the minus log n is just the same. If we use the logarithm rule, this is 1 over n, but this is just n to the minus 1. This is also an inverse polynomial. This is not negligible. Right, next one. 2 to the minus log square n. Is that a negligible function? Well, let's check it out. Let's for a second assume that it is negligible, and we have 2 to the minus log n squared is smaller than n to the c. Let's take a logarithm on both sides, and we get minus log n squared is smaller than c times log n, which is of course equivalent to log n squared greater than c times log n. And yes, this is the case for a sufficiently large n, so this function is negligible. Well, okay, further we have f4 is n to the minus log n. Let's do the same thing. Let's see whether n to the minus log of n is smaller than n to the c. Again, n to the minus c, that was here, here, and here as well. And let's do the same calculation, and we will have, by computing a logarithm on both sides, we will have, and multiplying by minus 1, I'm gonna speed up a little bit here. We'll have log of n times log n, that's minus the logarithm of the term on the left side, is greater than c times log n. And again, that's true because log n times log n grows faster than constant times log n for any constant c. So yes, this function is also negligible. And we see a simple rule, right? A function f is negligible if and only if minus log f of n grows really faster than log n. Here we have a lemma which simplifies working with negligible functions. It says that if nu1 and nu2 are negligible functions and p is a polynomial, then nu1 plus nu2 is negligible and p times nu1 is also negligible. Let's quickly do the proof. For the first statement, let's say p is any polynomial. I could also call it q. Q is any polynomial. Then, since nu1 and nu2 are negligible, there exist n1 and n2 such that for all n greater than n1, I have nu1 of n smaller than 1 over 2 times q of n. This is just using the definition of negligible functions. And here, the polynomial that I'm using is 2q. And I can do the same with the function nu2. So for all n greater than n2, I have nu2 of n smaller than 1 over 2q of n. All right, now I just set my n to be the maximum of n1 and n2. And I get that for all n greater than n, I have nu1 of n plus nu2 of n is smaller than 1 over 2 times q of n plus 1 over 2 times q of n, which is, of course, just 1 over q of n. I showed that this holds for any polynomial q. So for any polynomial q, I have shown there exists a capital N, namely this one here, such that nu1 of n, such that for all n greater than n, nu1 of n plus nu2 of n smaller than 1 over q of n. Okay, that's the first part. For the second part, I'm using the definition again. And here I'm using a polynomial, I'll call it q prime of n, which is just p of n times q of n. And again, using that nu1 is negligible with the polynomial q prime, I'm getting that there exists a capital N, such that, again, for all n greater than this capital N, I have that nu1 of n is smaller than 1 over p of n times q of n. But now I just multiply both sides with p of n, and I get p of n times nu1 of n is smaller than 1 over q of n. So for every polynomial q, I can do this for any polynomial q, I found an n such that for all n greater n, p times nu1 of n is smaller than 1 over q of n, which shows that this function is also negligible. Now it's time for the full definition of computationally secure encryption schemes. Start with the syntax. An encryption scheme consists of 3 PPT algorithms, keygen and DEC, where, as remarked before, keygen now takes as input the security parameter encoded in unary. Still a randomized algorithm which outputs the key k. Encryption is maybe a randomized algorithm which takes a key k and a message m as input and outputs a ciphertext c. Decryption is a deterministic algorithm which takes as input a key k and a ciphertext c and outputs a message m. That's the syntax. In terms of correctness, we require that it holds for all security parameters lambda in n and all messages m, that the probability that if you encrypt a message M with a key K and then decrypt it with the same key, that you get back the same M is 1, where the key K is a random variable generated by the keygen algorithm. One remark, I haven't specified the key space, pardon me, the message space. So typically we assume that either the message space is 0, 1 or just 0, 1 to the security parameter. We have those are the canonic choices for message spaces, and in essentially all the schemes that will all the secret key schemes that we consider, the message space will be one of those two. Regarding security, what we want for computationally secure encryption is indistinguishability security against PPT adversaries. So the int experiment is almost the same as before, with the one difference that the experiment now depends on the security parameter, and so does, of course, the keygen algorithm, but otherwise the experiment still is the same. We have a PPT adversary. We now have a PPT adversary A, which announces two messages, M0, M1. The challenger generates a key, flips a random bit B, and encrypts the message MB, gives it to the adversary. The adversary does arbitrary PPT computations and outputs a guess B prime. If B prime equals B, the adversary wins, otherwise he loses. And we say that an encryption scheme, keygen encdec, is int secure if it holds for every PPT bounded adversary A that there is a negligible function nu such that for all security parameters lambda in n, it holds that the probability that int A equals 1, the probability that A wins, is smaller than 1/2 plus nu of n. Let's briefly discuss the pros and cons of defining security via asymptotic complexity. First, asymptotic security will allow us to base security of schemes on so-called standard assumptions via reductions. The main shortcoming is that asymptotic security does not tell us how we have to instantiate schemes concretely. That is, in practice, if you want to use it, how should you choose this security parameter lambda? Asymptotic security doesn't really tell you anything about this. But on the other hand, asymptotic security is typically a guarantee that a scheme has no design flaws. If there was some major design flaw, you wouldn't be able to construct a security reduction from a standard assumption. I want to mention there is an attempt at reconciliations, though this research program is called Tight Security and tries to study reductions which will provide concrete quantitative security guarantees. Time to wrap up. What have we learned in this segment? First, perfect secrecy or perfect security is both an overkill and can be insufficient. In the notion of computational security, we only consider efficient adversaries and require their advantage in winning the security experiment to be small. In asymptotic security, efficient adversaries will be characterized by PPT algorithms, and small advantage means negligible advantage. That's all. Thanks.